Hey everyone, we're here to discuss atmospheric pressure. Now, we've already discussed pressure a little bit. Um, so, if we have a bunch of over a surface, all right. So, if we have some sort of surface, that surface, um, so here's a surface. You can imagine that particles are bouncing off of that surface, and that little collision here is causing some amount of force. The sum total of that force spread out over that area is our pressure. Now, that's not what we experience it as. We experience it as some sort of like push or even a pull in some instances. But that's the way we're going to imagine it, that all these particles are just colliding here with the surface, and that all those little collisions end up pushing on that surface. So let's examine one of the demonstrations that we've done. Let's go ahead and take our Erlenmeyer flask. So we had an Erlenmeyer flask with two straws, one that was longer, one that was shorter. Ugh, oh gosh, I can do better than this. One that was longer and one that was shorter. And we're going to go ahead. I'm going to make a couple copies of this because we're going to use this for a few different things. Okay. All right. So we're going to go ahead and look at three different states of the Erlenmeyer flask. Now, normally the flask is just sitting here without too much issue. The water level just stays right there. Nothing big deal. But if I start putting extra particles in to the side here, and we put extra particles into this with a syringe, what we end up getting, let's kind of sort of zoom in on this spot. What we end up getting is a situation where there's now more collisions with the water outside, and there's fewer collisions with the water inside. So compare that to over here. So now there aren't that many collisions on the outside. There are still some collisions on the inside. And what we end up is sort of balanced forces. That the force downwards on the water is just outside the straw is just as strong downwards on the water inside the straw. Here, though, because we now have more particles in our container, because we have more particles hitting the surface of the water out here, and there's been no change to the inside, this is now stronger than this is, which means we end up getting this water down here being pushed up that straw some amount. Because all those extra particles on the outside hit down a little bit more, and those extra particles outside now are pushing down harder on the water here than they are inside. All right, let's look at the third instance, which is where we go ahead and, we'll use the word, we suck all the air out. So how does this work? First off, we'll talk about how that would even happen with your lungs in a second. But what we've seen here is that water again goes up, water again goes up the straw, but it has to be for different reasons because there's no new particles this time, right? In fact, all we're doing now is we're removing particles. So let's go ahead and again zoom in down here. How can we make this water go up without removing any particles? Oh, sorry, without adding any particles. Well, the thing is we have back to our original number of particle collisions, right? So I think I drew 3 over here. So there's still just 3 over here. But what's happening now is we've removed the particle collisions from here. There's now fewer particles inside this tube because, well, they've gone somewhere else. We'll explain that in a second. We've quote-unquote sucked them out. So now there aren't as many, which means I now, again, have a stronger force down than I do, stronger force down outside the straw than I do inside the straw. But instead of just making the outside force stronger, we made the inside force weaker. So again, the water goes up the tube. All right, this is a pattern that we see, that suction is not actually pulling on anything. Instead, suction just makes some other push relatively stronger. Suction is not pulling this liquid up the straw. Suction is just making the air outside the straw. If I can change the color. Suction is just making the air outside the straw strong enough to push the water up the tube. Quick little side note, how does suction actually work? So let's imagine the straw here, and we'll do kind of a simple straw. And then let's imagine that this is your face, you know, and you're sucking on the straw. And let's go ahead and imagine this going down to your lungs. All right, those beautiful set of lungs. Look at that. I'm such a talented person. And so let's sort of imagine what's going on here. We have particles bouncing around out here, but we also have particles bouncing around inside this tube. And then we probably also have particles bouncing inside your lungs, bouncing up and down your tube. We can imagine that this is happening, right? Well, what's going to happen when we increase the size of our lungs? So we use some muscle to make our lungs bigger. Is that lungs? Is that what lungs look like? Whatever, close enough. So, and then we had the straw, so we had the cup, and we had our face. This is kind of a disturbing picture now that I look at it. Ugh. Anyhow, what has happened? Well, we've given these particles more room. So now that these particles have more room, more of them are just going to go in the lungs. Not because we're pulling them, but just because there's more room. So there's just a greater likelihood that particles will end up in your lungs. So there will still be some particles in the straw, but more room means more of the particles end up in here, and fewer of the particles end up hitting the surface of your water, which again, if there's fewer particles hitting the surface of the water inside the straw, that will cause the water to go up. All right. So that was a quick little side note. All right. So I want to imagine something. So in this instance, we see what's actually pushing the water up the straw both times is not like us with a syringe. It's not us pulling somehow with our lungs. In both times, it's the pressure of the outside atmosphere. We call this the atmospheric pressure. And this was what's the case was in both of these. Both of these are just situations where the atmosphere are just pushing air particles up the straw. Now let's think about how strong this is. So I want you to imagine that we did the same setup. So we'll go ahead and take an Erlenmeyer flask, and we'll go ahead and make some straw. And then we'll have our second straw open to the atmosphere. If I remove all the gas from this tube, how high will it go? because I'm not actually pulling on this. I'm not doing much. Let's remove all the gas here. So let's go ahead and say a good example here is you have Superman. Look at his nice hair. And oh gosh, I'm not in the mood to draw a real body, so we'll just draw a cape and all that. So Superman is here. Superman has strong enough, Kryptonian lungs. He can literally get every single last gas particle of that straw, even though I don't think it's anatomically possible. But anyhow, he can get every single particle out of that straw. Remember, Superman is not actually lifting the water. The atmospheric pressure is lifting the water. So if he's not lifting the water, but air actually is, the air has a limit to how far it can actually lift it. Turns out for water, it's 33.6 feet. At 33.6 feet, that is as strong as the air generally is. Now, some days it goes a little bit higher, some days it goes a little bit lower, but 33.6 feet of water is as big as it can get. Now, I don't know about you. I would love to build one of these just to prove it's true, but we'd have to like go into the gym. That gym doesn't have a post on there, whatever. It's just on the wall, and like there's a scoreboard and the double doors, right? Well, this thing would end up going. We'd have to have like a little pool down here, and the straw would go all the way up to the ceiling, and maybe even a little bit past. I don't remember. And that'd be fun to build. I'd be up here on the roof like, yay, this sounds like fun. But it's a little impractical. So one way to do this is let's use a heavier liquid. Because, if air can pick up 33.6 feet of water, well, what about let's use something heavier so we don't need a 33.6 feet. So what we're going to end up using instead is mercury. Mercury is significantly more dense than water. Off the top of my head, I think it's 13 times the density. So if it's 13 times the density, that means we should need 13 times less the height. And sure enough, if you take a pool of mercury and you take a tube in it and you use some sort of vacuum to remove all the air from the tube, generally the mercury will make it up 760 millimeters. Now, some days the air particles will be a little bit more numerous and moving a little bit faster and hitting a little bit harder, and it'll go up a little bit. And some days the air particles will be moving, actually a little bit faster. They'll be a little bit less numerous. They'll be a little bit less dense, and the mercury level will go down a little bit. But in general, we call this 760 millimeters of mercury is pretty normal. We actually use this as a measurement. We'll actually talk about how a normal atmospheric pressure, that's 1 atm, is when it can hold 760 millimeters of mercury. So this is actually how we end up measuring pressure. If you were to go online and look at some weather report right now, you'll actually see a couple different things. You might see inches of mercury, but I think we can figure out the conversion there. You might see something called torr. You might see something called bar. There's a ton of different pascals. There's a ton of different units for pressure, but we're going to pretty much stick to these two. What I'd like you to know is that atmospheric pressure, kind of normal atmospheric pressure, is strong enough that it can hold up 760 millimeters of mercury. And that's a common measurement that we are going to use. I do expect you to have a concept of how the water is being lifted up the straw, not by Superman up here, but by the atmosphere, but by all the particles hitting off this surface, that even if you were to remove every single last particle, you can't get it past 33.6 feet. Which, by the way, if you want to think about it, there's a lot of buildings that are way more than 33.6 feet. So how do you think they get their water up here? When I have my rooftop jacuzzi. I don't know how to draw a jacuzzi. Whatever. how do we get the water up past 33.6 feet? Well, there's got to be a way, and I'll let you think about that. All right, I'd expect you to be able to describe how something like this would work. What's actually pushing the water up the straw? Because it is not our lungs. Our lungs are just adding more space for the particles to go through, which means they're a little bit less likely to be in the straw. I expect you to have a concept of what pressure is, of how pressure works, of how it's just particles bouncing off of things, and I expect you to remember the units that we will be measuring pressure in. All right, everyone, let me know if you have any questions. Have a nice day.